Dear students, let's start lecture number 14 on the topic Feistel block cipher structure of the KUST network security. This is our outline. First of all, I revise lecture number 13. Then I'll explain why we need Feistel block structure. Then I'll explain important built-in blocks of uh, of a Feistel block cipher structure. Then I'll be explaining different processes of Feistel block structure like encryption, decryption, and number of rounds. Let's get started with the revision of lecture number 13 on the topic watermarking. Here you can see that we have a image and we have two parties. One is attacker and another one is owner. And both are claiming that this picture is mine. So how we can determine or how we can resolve this conflict of interest? So this can be resolved by using watermarking. If we watermark that image, so this watermark identifies that this image belongs to this particular honor. So using watermarking, we can provide the solution of ownership. So what the watermarking is? Watermarking is used to verify the identity and authenticity of the owner in the digital image. Now, watermarking is a process in which the information which verifies the owner is embedded into the digital image or signal. The signal can either be video, picture, or audio. Most of, for example, famous artists, they watermark their picture or images. If somebody tries to copy those images, the watermark is copied along with the image, and that image can identifies that who is the owner of that image or a picture. This is the basic building block of watermarking. So there are two processes involved in watermarking. One is called embedding and another one is called extraction. In the embedding, you embed original image to embedding algorithm, and you also feed uh, watermark and key to the embedding algorithm, and it generates watermark digital image. So watermark digital image in the process of extraction, this watermark digital image is fed to process of extraction, and it has the key already, so it will get the original image back. So embedding is performed at the sender side, and extraction is performed at the receiver side. These are the attributes of watermarking. So imperceptibility, so means this is not visible or noticeable in the image or in a big information. Robust means cannot be taken out easily by an attacker, so it can resist to any kind of attack. Security, no adversary can get it, and the complex me cannot be understood easily, because if this is not be understood easily, so the malicious or the intruder will not be able to get that watermark information. Verification need verification before actual information is provided. These are the types of watermarking. Means visible watermarking, as in name refers that it's visible on the image or a picture or a video. And visible watermarking are typically logos or a text. For example, you can see a TV broadcast, the logo of the broadcaster uh, visible right side of the image. Whereas in invisible watermarking refer to adding information in a picture, audio, or a video that is not visible or perceivable, but it can be detected by different means or by different softwares. may be used to form the type of steganography and is used for widespread use. Can be retrieved easily. Public watermarking means that user of the contents are authorized to detect a watermark, whereas in private watermark, user cannot authorize to detect the watermark. Symmetric means same keys are used for the process of embedding and detecting a watermark or extracting watermark, whereas in asymmetric watermarking, different keys are used for embedding or detecting watermarks. Robust watermark means modification of watermark content will not affect watermark. Fragile watermark means get destroyed when watermark content is modified or tampered with. Steganography watermarking, user unaware of the presence of a watermark, wherein non-steganography watermark, user is aware of the presence of watermark, and it's is user for used for detect privacy. These are the applications of watermarking that is used for copyright protection and used for source tracing, whom that picture, video, or an audio belong to, annotation of photographs, and broadcast monitoring. These are the applications of watermarking. This slide shows comparison between watermarking and steganography. So the scope of watermarking provide ownership, whereas the scope of steganography is to hide secret information. The input data to watermarking is image or video or multimedia, whereas input data to steganography is any kind of digital data. Uh, secret data, secret water in watermarking, secret data is what we call it as a watermark, whereas steganography secret data is called stago data. Sorry, this is not a payload. This is stago data. Output data is called watermark data, and output this called payload. Protection of watermark gives protection to the original image, whereas steganography gives protection to the secret information. Imperceptibility in watermark require only the visible watermarking techniques, where steganography it is highly required. Robustness in watermarking, this is highly required, whereas steganography, this is desirable. Payload capacity is moderate, and whereas payload capacity in steganography is very high. If you remember that I have discussed this point in my previous slide, that payload capacity means that how much data you can input into your data or the image. So if you remember that in steganography, if you input more data, so it get the attention of the malicious user that there is something wrong in that, so he can get the attention of the malicious user, whereas in watermarking, you can put as much data as you want, so there is no problem in watermarking. The challenges of watermarking are high robustness and good imperceptibility, whereas challenges of steganography, good imperceptibility and highly payload capacity. These are the challenges of steganography. Summary: watermark is a process in which the information verifies owner is embedded into digital image or a signal. This signal could either be video, picture, or audio. Steganography is changing the image in a way that only sender and recipient are to detect the image. That what is being sent, so intended receiver can only get that information. Watermarking is of two type. I have explained these already: visible and invisible. And steganography, this is typically invisible. Now, let's start lecture number 14, which is our today's lecture on the topic Feistel block cipher structure. So, uh, before explaining this slide, I want to give you a brief about block cipher. If you remember that when we were converting our plain text to cipher text, there were two operations, generally two operations, which are normally used to convert your plain text to cipher text, and they were uh, uh, stream cipher and block cipher. Stream cipher applies on each character of your plain text, whereas block cipher applies to more than one character at a time to convert your plain text to cipher text. As we have a number of block cipher available, so the question is that why we need this block cipher. So they are actually not secure. The existing block ciphers like Hill cipher and Place cipher, they are not secure and can be brute forced by a malicious user and can get your confidential information, which is very dangerous. So we need some kind of a more secure and reliable block structure. So Feistel block cipher structure is normally used to create more secure and reliable structure. Now, Feistel block structure, as in this is not a specified scheme of a block structure. Actually, this is a model or a design. Using that, you can create many different kind of a block structure as per your desire. DES an example of a Feistel block structure. A Feistel block structure uses a same algorithm both for encryption and decryption. Like if you, as we will be studying DS in our next class, so DS uses same algorithm for encryption and decryption. These are the processes which are involved in Feistel block structure, like encryption process, decryption process, and number of rounds. So let's start with the process of encryption. In the process of encryption, you have an input. As this is block structure, so you will be considering more than one character at a time. So in a input block is divided into two halves. So one is called left half and another is called right half. You can see this the same in your picture here on the right side of this slide. So you have a plain text on the on the top. So we have divided plain text into two halves. One is called left half, another one is called the right half. So left half and right half. So each in each round, the right half of the block goes through unchanged. You can see here that right block is going to the next block without any change. So we can say that goes through unchanged. In the left half, if you see the left half, so you have to perform, like you can see that you will get the R here, and you need a key here, and then you will perform the process of encryption, and then you will or the output of this encryption, you will OR with the left side or a left half, and then you will provide the output of the left to the right side of the next or to the next round. So apply the encryption process. So takes two input, K and R. K and R, these are these are involved in the process of encryption. And then you will XOR the output of the mathematical function with L. So with the left side, so the output of this will be provided, or this will be XORed with the left half of this block cipher. So here you can see that in in real time, real implementation of the Feistel block cipher, such as DS, instead of using the whole encryption key at once, during each key a round dependent key. You can see here that here keys are mentioned, but remember that they are not same. They are the sub keys, and they are derived from the encryption key, which is you can call as a master key. Each round uses different key. Sub keys are related to the original key. So you can say original key as a master key. So on each round sub key will be generated from the original key, and then the permutation step is performed at the end of each block. So in the permutation step, swapping is being done. You can see here that R is goes unchanged, where on the left you get the R and the sub key which is generated from the original key, and then we XOR and passes to the next round right half. So and then you may call it that this is a process of permutation. Like substitution is done here in the round, and at the end of each round permutation is performed. So swapping is done. Right value will be passed to the left one, and left half value will be passed to the right one. So using that, encryption process will be done. So substitution and permutation steps form a round. So on each round you have a substitution and permutation steps, they are performed. The number of rounds is specified by the algorithm design. So that depends on the algorithm. Like DES uses 16 rounds. We will be studying in our next class. But each algorithm, as this is a model, but it depends that it gives you a general overview of that what number of round will be considered by that specific algorithm. So once the last round is completed, the the two sub blocks will be generated like L and R, and they will be concatenated to form the cipher text. If you remember that at the beginning we have divided the plain text into two halves, left half and the right half, and after each block performing the process of substitution and permutation, when it passes through the number of n rounds and reaches at the end of this process, you will get different blocks. Like one is at the left, one is at the right. So we can concatenate these two to get the block cipher at the end. Now, this is a formula that how the encryption will be done. Like you can see here that the how the L will be received, like second of L will be received of the first of R. For example, if you replace I with with uh, 1, so L2 will be R1. So you can see here that this is L2 and this is R1. So this is how the encryption is done. I've explained this that uh, that L will be the previous round R. This is explained here in with this formula, and with this formula you can see here that how you will get the next R. You will get the previous L with the XOR function with the encryption of a sub key and R, means previous R. So if you perform the encryption of this plus XOR with the previous L, you will get the next R. So I have explained this, that you will perform this. You have a R, you have performed here encryption and then XOR, and this will be provided to the next round R. So how you will get this? These are the formula for encryption. Now Uh, in the process of decryption, you can see here, I have explained this process from bottom to top. So you will get the ciphertext. So instead of plain text, now you have a ciphertext will be input at the receiver side. As you know, that sender has received plain text and has divided the plain text into two halves, and then perform R will be passed to the next round, to the next L without any change, whereas on the L you perform the process of encryption on the R plus the sub key generated from the original text, and XOR with the left to provide it to the next round R. But here in Cipher, process of decryption, ciphertext will be received, and this ciphertext will be converted into plain text again. So how it will be done? So the ciphertext block is fed into the start of Feistel block structure, as this is the process of decryption. So so the ciphertext will be received. The process thereafter is exactly the same. uh, the process is divided in, like we have divided the plain text into two half, like similarly we will divide the ciphertext into two halves, like one will be called left half and another will be called the right half. but but the process will be in reverse order. Like for example, at the process of encryption, right was going unchanged, whereas in the process of decryption, left will be going unchanged, and on the right you will be performing the on the right you will be performing the process of encryption by getting sub key and the key of left. You can see here key of left, and XOR with right, XOR with right to pass to the pass to the right. So this way you will convert your ciphertext to plain text. So the process is said to be almost similar and not exactly the same, as I mentioned, that the only difference that sub keys used in encryption are used in reverse order. You can see here that you will reverse these keys, and you will perform the process in reverse order, like what you were performing at the left side in encryption, that will be performed on the right side of decryption, and what you will perform at the right side of encryption will be performed at the left side of a decryption process. The finally swapping process will be performed on left and right, and if this is not swept, the resulting cipher could not be deciphered using the same algorithm. Remember that this permutation is also very important to perform to get your plain text. Now, these are the formula for decryption. Like here you can see that on the next of L will be the previous of R, and here you can see that on the left side of I means 1, means here you have the right side, you will perform the reverse operation which you performed in the encryption. This is the reverse operation which we performed in the process of decryption. Now, the number of rounds used depends on desired security from the system. Advantage is if you use more rounds, so we can say that our system is more secure. Like DS uses 16 rounds. So if you use 18 rounds, so you can do that because this is a general layout, and considering this layout, you can use any number of rounds. And the general phenomena is that if you use more rounds, so your system will be more secure. But for any for any for any operation, there is a trade-off. If you're using more rounds, so your system will be secure, but more round means inefficient because you need more processing power for encryption and decryption processes. So the number of rounds in each system depend on the efficiency or security trade-off. This is a trade-off that if you consider, so where is the threshold that where you get the maximum of your maximum security and and the least processing. So as I mentioned, that DES uses 16 rounds. So on one side it provides you security, but on the other hand it is inefficient if you use more rounds. So this was about Feistel block cipher. So these are the sources cited. You can please visit those sites to explore more about this topic. So if you have any question, you can ask me through KCMS or WhatsApp, or you can email me. My email is listed at the bottom of the slide. You can use my email to question me. I'll be more than happy to answer your questions. So with that, it brings us to the end of this lecture. So till next lecture, Allah Hafiz.